So, logarithmic functions. All right, so take a look at this. I have here some powers of 2, right? So 2 to the power of 1 is 2. And then I raise the exponent by 1. 2 to the power of 2 is 4. And then if I raise the exponent one more time to 2 to the power of 3, I get 8. But what happens when I raise my exponent from 2 to 3? The value, the power, increases dramatically, almost from 4 to 8, right? I skip over all the numbers between 4 and 8. What if, though, I was looking for an exponent of 2, so that 2 to the power of that number would give me 6, right? When I went from exponent of 2 to 3, I missed that, right? I went from 4 to 8. So what are some predictions for the exponent of 2 that would give you a value of 6? Yeah. Right? So it could be 2.5. Now, does anybody have their calculator with them? Plug in 2 to the power of 2.5. Okay, so it's not quite 2.5. So what do you guys think then? 2.7. Okay, so try 2.7. 6.49. Okay, now you went over. So what do you think? Okay. 2.65. Okay, still over. So now, okay, so you could do this all day and, go, above and below a certain number and try to figure out the exponent, right? So basically, what is it that we're looking for? We are looking for an exponent, right? The exponent of 2 that would give you a value of 6, all right? Well, believe it or not, that is a logarithm. To answer that question, you need a logarithm, all right? So one way I can ask the question is, what is the exponent of 2 so that 2 to the power of that exponent is equal to 6? Now that's a mouthful to say every single time. So I could either say that long sentence, or I could just say log base 2 of 6 equals what? And that means the same exact thing. So if I were walking down the street and I saw that on a billboard, log base 2 of 6, I will immediately think to myself, oh, somebody's looking for an exponent of 2 that would give them a 6. Okay? That's what that means. All right? So now, here's my question to you. What were we looking for here? A what? Starts with an E? An exponent. So if you have a logarithm, what is the answer to a logarithm always? An exponent. Okay? A logarithm gives you what? An exponent. All right? Here we go. Okay, so now, in order for you to have a power, right, you need a base, an exponent, and then the power, all right? So, base, exponent, power, all right? Here, in this logarithm notation, look, you've got the same thing. You've got a base, a power, and the exponent. You see that? The key players are the same, but rearranged. All right? So now, when we do these exponents, when we do these logarithms, I need you to always think in terms of exponents. I know there are lots of shortcuts out there, and I know of all of them. The snail method and the this method and the that method, and those are fine. But for our purposes in pre-calc honors, I really want us to think in higher terms, in terms of exponents. Okay? All right. Now, you see then that we can write the exact same relationship in logarithmic form and in exponential form. Okay? And this is all stuff that you've seen before. I know that. All right. So, in logarithmic form, the relationship is written like this. Log base b of x is equal to y. And the logarithm always equals the exponent. You have the base here, and that's your power. Okay? Yes? And here, right, so this is the logarithmic form. If you want to write it in exponential form, you need a base. Every base needs an exponent, and then that's the value of it with the exponent. Okay? Now, if logarithms are just ways to get an exponent, right? If the answer to a logarithm is an exponent, then it makes it so much easier for us to remember the properties of logarithms. Again, I don't want to see anybody memorizing any of these properties, because if you've memorized, it doesn't mean anything. You've got to understand. When you understand, you will never forget. Okay? So here we go. Let's talk about properties of logarithms. All right, let's do this one. Log b of 1. Okay? What is this number here? That's a base, right? And this is the answer. This is the power, right? So what is this question saying? If you saw this on a billboard, you know what? Let me make this a 2. If you saw this on a billboard, what would you say it's asking you? Find the exponent of 2 that gives you 1. So basically this is asking me 2 to the power of what gives you 1, which is 0. Okay? So if I have log base 343, 1, that equals what? 343 to the power of what gives you 1? 0. So log base b of 1 equals b to the what gives you 1? 0. All right? So that's why everybody always tells me, I can never remember, is log of 1 0 or 0 or 1 or whatever? Well, okay, so you're asking b to the power of what gives you 1? 0. Okay? Next one. B to the power, okay, so look at this one. This is asking you b to the power of what gives you b? 1. Okay? So it's not that these things cancel each other out, blah, blah, blah. That's what it is. B to the power of what gives you 1, gives you b? 1. Okay, take a look at this. Here. Let me write it here. Log base b, b to the x. Okay? Look at this. This is the base. B to the power of what will give you b to the x? What if, right?
Oh, because it's like if you switch it, so b to the x equals b to the y.
Right, so what should the exponent of this equal to so I get b to the x? X, all right? So that's why the answer to that is x. Do you see how simple it is, how trivial it is if you just reason it out? There's no need to remember. There's no need to do some snail, whatever it is that people do. There's no need, because it just makes so much sense in the math, okay? All right. So now, logarithms can have any base whatsoever. Anything could be a base of a logarithm, a 2, a 343, a b, a whatever. The most common, okay, so where are logarithms used? Where is a logarithmic scale used? What's an example? Where do we use logarithms? Do you know? What's the, okay, the most common example, the most widespread in California where we use the logarithms is the Richter scale. What does the Richter scale measure? Magnitudes of earthquakes, right? So it takes the intensity. The intensity is in the tens of thousands, but what are the magnitudes in? 1, 2, 3, 4, all right? Where did the 1, 2, 3, 4 come from? These are exponents of 10. So the most common base of a logarithm is a 10. All right, so if you take common logarithms, now look, base 10 is so common that we don't write it. All right, so for example, if I have 1x, do I ever write the 1? No, because you just know. So now, log base 10 appears so commonly that we don't have to write the base 10. In short, we just write log of x, okay? So if I have log of something with a base missing, it's not a typo, it's always a 10, okay? So now, if I have this one here, what's the base? 10. 10 to the power of what gives you 1? 0. All right? Here, the base is a 10. 10 to the power of what gives me 10? 1. All right, so that's how you reason through these. 10 to the power of what? 10 to the x, and so on. Okay, so those are common logarithms. We'll go over the very last one.
And also decibels is measured.
Decibels as well. Decibels are how, again, it's intensity and then level of sound, noise level. Okay, so let's do some of these here. Evaluate each logarithm. So obviously these would be ones where you would not have a calculator handy to do these, right? So log base 2 to the 16. So basically, again, what is the exponent of 2 that gives you 16? 4. Okay? All right. Here, 125. 1 over 125. All right, well, 125 is 5 cubed, right? 125 is 5 cubed. But what about 1 over 5? It's negative, right? So this is log base 5, 5 to the negative 3. So that's negative 3. Okay, so because the fraction, the 1 over, the reciprocal, happens when you have a negative exponent, you should just, know that if you have a base, whole number, and then it turns into some reciprocal, then there is a negative exponent there. So I just say, okay, 5 cubed is 125, it's negative 3. Okay? This one here, log base 3, and then what's cube root of 3?
1/2.
3 to the 1/2, right? So basically, what should be the exponent of 3? So you get square root 3, 1/2. Okay? What about this next one? Log base 8.
Just the third, 3.
Yes, 3. All right. So, all right, this one, same situation. I'm going to go over it later. But basically, you've got a base to the power of the log with the same base. And what you end with is just the 15.5. It's the same situation. You're looking for the exponent of that one. Okay? Here, what is this? What's the base there? 10. So 10 to the power of what gives you 10,000? 4. Right? 10 to the power of 4 is 10,000. So if you have an earthquake with a magnitude of 4, the intensity of that is really in the 10,000s. Okay? I'll talk more about that later. All right, here, same situation. What is this going to be? 12. What about this one? Log base 10 of 14. This you can't do manually, so I'm going to ask for you to plug it into your calculator. Go ahead and do that. Log of 14. 3 decimal places always with logarithms. 1.146. Okay, so the next one, don't plug it in yet. So it's 1.146. Don't plug in the next one. Okay, what is the base of the next one? Number I, it's a 10. So now you're looking for an exponent of 10, which would give you negative 12. Why isn't it possible? The exponent can never make the value negative. Think about it. 2 to the power of a positive number is a large number. 2 to the power of 0, 1. 2 to the power of like minus 5 does not become negative? No. And remember with our exponential graphs, when we explored them yesterday, the values would go down, 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 reach exceedingly close to 0, but never cross that 0. So that's just never possible. So you see how when you think of these in terms of exponents, it's so much easier for you to remember. All right? It just makes sense to me in my mind. Okay? All right. Now, we said 10 was the most common base, but the soulmate of the logarithm is e. The base e. All right? In fact, they are so good together. There is just a natural relationship. So when the base of the logarithm is e, we call it a natural logarithm, or ln. Okay? And we talked yesterday about why it was ln and not nl, right? Because it's in French. Okay. So if I have log base 10 of, I don't know, 5, I write that as log of 5, right? We're good with this? Now, if I have log base e of 5, then the whole thing is just ln of 5. So ln is just log base e. It's nothing different. It's just log base e. It's still log, all right? It's not a different quantity. It's not a different operation. Exactly. So a lot of people think log and ln are different operations, but they're not. It's just a different name for it. Just like log base 10, we say log. Log base e, we say ln. Okay? So if I have ln of 5, I'm still looking for e to the power of what gives you 5. Okay? So here, take a look at this one. What am I looking for here? E to the power of what gives you 1? 0. Okay? E to the power of what gives you e? 1. All right, there is a base of e here. This is log base e of e. So it's 1. Okay? So what about this one then? ln of e to the 4.5? 4.5. ln of negative 2 doesn't exist. I'm yelling because I'm excited. I'm feeling it here. Okay. E to the ln of 4 is just 4. ln of 7, this is a calculator one. Somebody help me out here. We don't want around, we want precise.
1.946.
Good, yes. Okay, 1.946. All right. So, all right, so let's talk about graphs of logarithmic functions. So we just said, yesterday we talked about how to graph exponential functions, b to the x, right? So y equals b to the x. Now, with logarithms, what are we solving for in here with the logarithm? What does the logarithm give us? The exponent x, right? So instead of one variable, it gives us the other variable. What do we call it when these variables are swapped? Inverse, right? So logarithms are the inverses of exponential functions.
When you multiply one number by its inverse, one thing by its inverse, do you always get 1?
That's a multiplicative inverse. Here we're talking about like functions being inverses of each other. Okay, so suppose I were to graph y equals b to the x. Where is there an asymptote? At y equals 0, there is an asymptote, right? So it would look like this. And then, okay, so what's the y-intercept here? When x is 0, y is what? 1. So this is a graph of y equals b to the x, right? Now, if I draw the line y equals x, take a look at the blue. The blue is y equals log b of x. So do you see how b to the x and log of x are inverses of each other, right? So take a look. What's the intercept here? X is 0, y is 1. What's the intercept for the other one? 1, 0. All right? Where is there an asymptote here? It's the x-axis. Where is there an asymptote here? It's the y-axis. Okay? So, for y equals b to the x, what was the domain?
All real numbers.
All real numbers. B to the x. What was the range? 0 to infinity. For the logarithm in the blue, what's the domain? Domain is 0 to infinity, and the range is all real numbers. So what happens? Just as inverses do, the domain and range will switch. Okay? All right. So this here is an example of logarithmic growth because, you know, you could see it's growing. How quickly do exponential functions grow? Very, very quickly. Logarithmic functions grow very, 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 very slowly. Okay? This is logarithmic decay because it's decreasing slowly but surely. It's decaying. All right? Okay. So now, to graph logarithmic functions, we're going to use the properties of it. Go back here to the very, very first thing we did. Okay? Look at these y values here. What's the y value here? 1/2. What about here? 1, 2, 4. Do you see that even yesterday we were graphing the same thing? Yesterday, the powers were on the y-axis. The exponents were on the x-axis. Well, now if we're going to graph the inverse, what happens?
Swap them.
It switches. So the exponents are going to be on the y-axis and the powers on the x-axis. You guys are not as excited about this as I am. I don't know why, but this is like super cool stuff, okay? I don't know what other way to end the week with than this. Okay, so here's what we're going to graph now. But now, I'll get you. Now the powers are going to come here and the exponents are going to go over there. All right? Question?
I was saying, can we just think of it as like 2 of x?
Yeah, that's exactly what we're going to do, Aiden. That's exactly what we're going to do. Exactly what we're going to do. Yes?
So, is the logarithmic growth and is logarithmic growth just...
If I write this way, look, the same exponent, the same function, if I write it this way, log base 2 of x equals y, what does the y represent? The exponents, right? Okay, so now, where is there going to be an asymptote? We said the asymptotes were vertical here, so it's going to be at x equals 0, right? So at x equals 0, this is going to have an asymptote. And make sure your asymptotes are visible. So again, put it like a hair to the left or to the right, but make sure I see your asymptotes. Okay, so now the x's here, it's horizontal this time. I'm sorry, it's vertical this time. Because it's a logarithm, the asymptote is vertical. Okay? All right. So now y is going to have the exponents, right? So what we do here is we want the exponents in the y column. So the exponents, we're going to do -1, 0, 1, 2, 3. And these are going to be our powers, right? So here the base is 2. 2 to the -1 gives you 1/2. 2 to the 0, 1, right? So these are the powers of 2. 2 to the 1, 2 squared, 2 cubed. So 2, 4, 8. Okay? So always remember that y is the exponent. So these are the exponents here on the y-axis, and then your powers are going to be on the x-axis. So now, when x is 1/2, y is -1. When x is 1, y is 0. When x is 2, y is 1. When x is 4, y is 2. And then when x is 8, y is 3. All right? And it's going to go this way. Okay? All right, so that's the only difference here. All right, domain, 0 to infinity. Range is all reals this time. Weird. Okay? X-intercept, 1, 0. No y-intercept. Okay, here we go. Take a look at this. The limit, let's do the bottom one first. As x approaches infinity, f of x approaches positive infinity. But now I can't, okay. So because limit looks from left and right, if I want to do the limit as x approaches 0, technically I can't do that because I can't look at it from the left and the right. So I only say x approaches 0 plus from the positive side, it goes to negative infinity. Okay?
So you didn't leave it on it for x.
Oh, here, negative infinity, sorry, huh?
Wait, so you can leave on it then?
You can do a one-sided limit. It's called a one-sided limit.
But you didn't make it known that it's one sided limit.
I did. You see here, it's on your paper, it's 0 plus. Okay? All right. Next one, we have this one here. All right. So here, my base is 1 over 3. Again, asymptote is going to be x equals 0. Now, my base is 1 over 3. So if it's a fractional base, right, just like growth and decay, I go from negative 2 to 2. All right, so here it's going to be 1 over 3 to the negative 2. How much? 9. And then 1 over 3 to the minus 1. And then 0, 1/3, 1/9. All right, asymptote. Okay. I'll put the asymptote here. All right, I can erase it. Okay, so when x equals 9, y equals negative 2. When x equals 3, y equals negative 1. When x equals 0, y equals 1. When x is 1, y is 0, sorry. When x is 1/3, we're at, what did I do here? Sorry. I'm trying to rush because I'm running out of time. 1/9, we're at 2. Okay? There we go. All right, next. So, domain, same situation, 0 to infinity. Range, negative to positive infinity. X-intercept, 1 and 0. Okay, what happens as we approach 0?
X goes into, y goes into infinity.
Positive infinity.
And from the right side. Yeah.
Right? And here? Negative infinity. And it's continuous everywhere on its domain. Okay.
You put 0.
Huh? It's continuous from 0 to infinity. Everywhere on its domain. Its domain is 0 to infinity.
Domain is where.
So, okay. I said everywhere on its domain. You probably heard everywhere. Okay. Yeah. It's not. It was my pen was it dragged the ink or whatever. Okay. Now, here we go. Here we have ln. What is ln? And it comes from log of e. So technically this is just log base e x minus 6. So here I have log 1/3 of x. Here I have log e of x. So you see how like they're not much different, right? It's just that the bases now are just e. Now, what does the minus 6 do since it's with the x? Where does it move it? Vertical, horizontal? Horizontal, left or right? Thank you, right 6. So now, whereas the asymptote, the vertical asymptote was at x equals 0, now it's going to be at x equals 6. Okay? So, let's do, okay, so here these are the exponents, right? So this, let's do this one because it's easier to wrap our head against. So here essentially what I have is e to the 0, right? But it's going to move over 6 units to the right. All right? So let's think of it again. You see how these are the powers on the x-axis? Right? These are the powers. So here it's going to be like e to the x plus 6 essentially, right? So e to the 0 gives you 1, but you're going to add 6. So it'll be 7. Okay, everything will move over. Okay, e to the 1 used to be, it's 2.7, but we're going to add 6, so it's going to be 8.7. E squared, remember I said you're going to learn that it's 7.4 and eventually, plus 6, 13.4. And then here we're going to have e to the negative 2 plus 6, e to the negative 1 plus 6, and those values are 6.13, 6.4. No, I did it before. I'm saving time. So again, when you have an E related graph, you will have it on the calculator section. Yeah. Yeah, because all those word problems and stuff, you can't do it without a calculator anyway, right? All right, so basically, when x is 6.13, we're at negative 2, 6.4, negative 1, and then 0, and then 8.7, and then 13.4. It goes off the graph, so this is good enough for me. Okay? All right, here, the domain. What's the domain? 6 to infinity. What's the range? The x-intercept is 7, 0. Here, it should, I copied and pasted, this should be 6 from the positive side. As x approaches 6 from the positive side, it goes to negative infinity, positive infinity, and it's continuous from 6 to infinity. Okay? Now, I didn't get to this. Class ends at 9:55 today. So what I want you to do, still do the homework. All right? You can skip the word problems. If you don't get them, try them, okay? I have faith that you might be able to work through them. If you find that you're having trouble, skip them, but I do expect that you do everything else other than the word problems. You have until the test to finish it up and turn it in anyway.